Version control in hardware engineering can be quite difficult. And unfortunately, KiCad does not support any kind of version control to create multiple revision of the schematic or the PCB layout. So in this video, we'll see how we can solve this version control problem using Git. Imagine working on a large project where features are constantly added and changed. If it's not tracked at some point, we'll lose a lot of vital information like why was the feature added, why was it removed, and how did it affect the circuit. This is why we need version control, which helps in keeping track of changes made to the design. It's essentially like a database that stores every change made to the design over time. This will include addition, deletion, modification, and everything in between. So working on a large project, whether it's a software or hardware, not using a version control is like missing out on one of the most important tools that a professional needs. There are several popular version control systems, but Git is by far the most famous and the popular one, which is used both in hardware and software engineering. Importantly, it does all the features that we discussed for a version control system. But there is a huge caveat. This version control system works perfectly only on text-based documents. If you add a feature like PDF or an image, it cannot keep track of the features that's added or removed. It can only keep track of the number of revisions that's made. So first, let's try to figure out how KiCad handles its various file extensions like .kicad_sch, .kicad_pcb, etc. When we open any of these files in a text editor like a notepad or VS Code, we can see all these files are just made of human readable text, and there is nothing fancy. If you put some effort and learn what does these text mean and how KiCad generates graphical output based on these texts, we can directly perform edits on schematic and PCB layout editor just using the text editor without using KiCad. This is really good because it's very compatible with Git and we can see all the edits made on the text level. It's also possible on the graphical level, but we need to use additional tools along with Git to make that possible, which we'll be seeing in upcoming videos. I hope until now you understand why we need version control and Git. Now let's see how to install and use Git within a Windows machine. To install Git, go to git-sam.com and click on Downloads and here select Windows. Finally select the setup file that's compatible with your machine. Once the download process is done, go through the installation. To finish the setup for Git, we need to enter a username and an email. To do that, launch the Git bash after the installation. Here we can use this command to give the username and this command to set up the email. This completes the Git setup. From here on, we can either use Git bash along with various commands to make changes and track revisions. But it can be little hard to understand for people who are just getting started. So we'll be using the GUI version that Git offers. Git GUI is way easier to get started for beginners and very easy to understand. So in this video, we'll use Git GUI to understand how Git works and how to use it with KiCad. Git version control works on 3 stages. First, we have unstaged. In this stage, Git just observes the file that are not tracked or files that are just added in the repository. To make Git aware that we need to track these files, we need to stage it. And this is where usually we might review our work and see if everything is good before making these files or changes into a new revision. Once we finish our review, we can commit these files into a new revision with a meaningful message. And Git will save this as a new revision with a unique hash, which can be used to differentiate or revert back to the previous commits. Now we need to follow this process each time we make a new revision or a change to the circuit. Let's see how it works in action. We'll create a scenario where we are working on a project for a client, where he wants us to create a simple LED circuit with a given specification. So we'll fire up KiCad and start a new project. And we'll try to make this as our initial version for the project, where we have no schematic diagram, nor we have the PCB layout. But currently this is not tracked in any way. So let's open the Git GUI. Now in this Git window, click on Create New Repository. And now select the folder where KiCad has created our project. And then click on Create. This Git window is divided into 4 sections. On the top left, we'll have all the unstaged files, And on the top right, we have the viewer to see what's inside the files. And on the bottom left, we have the stage files. And on the bottom right, we have the commit message editor, where we can enter a meaningful message before we make a new revision. Currently, you can see we have these unstaged files since we just created a project and we never mentioned Git to track these files. To make Git track these files, click on Stage Changed and then click on S. This will move the files from unstaged to the staged area. Now we can enter a meaningful message here. I'll call this initial commit and then click on commit. This will save the first revision for our project, which has an empty schematic editor and an empty PCB layout. Similarly, I'll create a new commit for each feature I add to the circuit. I'll start with creating a simple LED and the resistor circuit. I'll save this circuit and click on rescan to detect the changes and then click on state changed. And finally, I'll add a meaningful message and click on commit. Now similarly, let's add a switch to the circuit. Finally, I'll add a battery to the circuit and perform a fourth commit. In case we did not use Git at this point, we have to either delete the battery, print a PDF, then add the battery again. Or we have to duplicate the project just like how we did in the KiCad series. But luckily, we made every revision using Git. So go to Git and click on repository on the menu bar. And under here, select visualize mains history. This will have the list of commits that are performed and also it will point to the current version or the revision that we are at. Since the client wants only the LED, resistor and switch, I'll select the third commit where we don't have the battery. And then copy the first 8 digits of the hash. And close this visualizer window. In the main Git window, click on branch and then select checkout. Here select the option revision expression and paste the 8-digit hash in the text box. And then click on checkout. You will have this pop-up which says this detached checkout. Just click on OK. And here in the bottom we can see the project has been checked out to the previous version. To confirm that, let's close this existing schematic and open it again. Seems like we have successfully went back to the previous version. Let's quickly make a PDF and send it to the client. While the client is reviewing, let's get back to the most recent version. Again, open Git, click on branch, click on checkout, and under this, select local branch and make sure main is selected and click on checkout. And this will get us to the most recent version of the project. To confirm, we can go to the visualizer, click on repository, under that click on visualize mains history. And here we can see the main is pointing to the most recent version with the battery cell added. We can also double check this by going to the KiCad project. I'll close this existing circuit and open the schematic editor again. And you can see we are back to the most recent version of the project. Even here we can do the changes to the circuit and make a commit. But whenever there is a test or an unsure feature, it's better to create something called as branch. This will help us create a new set of revision without breaking the existing revisions we have. Let's see in action for better understanding. So I'll go to Git and click on branch and under this click on create. And here I'll name the branch as to underscore LED underscore branch and then click on create. This will automatically create a branch and check out to LED branch. If you try the visualizer at this point, we can see both the main and the LED branch pointing at the last feature that was added. So I'll add the components as per the specification and make the commits as usual. Since our main branch is untouched, it's pretty easy to go back and get the circuit for 1 LED plus 1 battery and send it to the client. Since we are confirmed with the feature branch, we can merge that with the main branch. So go to the main branch and select merge and then click on local merge. And under here, make sure the local branch is selected and select the branch that needs to be merged. In our case, it will be 2 underscore LED underscore branch. And then click on merge. And here we can see I've successfully merged the 2 LED branch to the main branch. Now let's see how the version tree has changed after merging the branches together. Go to repository, click on visualize main history. And here we can see the main branch has been updated to the second battery added. So now when I go back to the mains branch, I'll close this and open the schematic again. And here we can see the main branch has all the feature that was added in the second LED branch. Now this process can continue forever throughout the development until the project is satisfied. By now you should be familiar with how to use Git GUI and how to visualize commits. Because of its simplicity, it's highly preferable for beginners. But it's not quite an efficient way to use Git. So let's see how we can use Git in the command line instead of using the GUI version. First, let's start with creating a new KiCad project. Once it's created, open the project in the File Explorer. We can do this by right-clicking on the project icon and then clicking on Open Directory in File Explorer. In the previous videos, we used to include all the files that's within the project. Some of them are not necessary to be version controlled. For example, this cache file. To avoid these files and not include them in the version control, we can create a file called .gitignore and give a list of files and folders that needs to be avoided. We can do that by opening git bash and using this command. Once the file is created, open the file in a text editor and enter the list of files and folders that needs to be avoided during version control. And then save the file. If you like to use the same list, I'll put a link in the description where you can download this. Since we have created the gitignore file, let's track this folder by using git bash. So open git bash and type this command. This command will initialize the entire folder and track all the changes. Also, it will create a hidden file called .git folder which will have all the commits and the tracking details. Unlike Git GUI, in git bash, there is no visualizing the commit tree. So to see at what stage the files are in, use this command. This will show the current status of the repository. Here we can see there are few unstaged files that are highlighted in red. And also if you notice, it does not include any of the files or the folders that's within the .ignore file. Anyway, now to stage these files, we need to use the command git add and followed by the file name. Let's try the git status again. Here we can see we have successfully moved the .ignore file to the staged area. But adding files like this stage by stage can be tedious. In Git, we can also move all the file at once by using the same command, but now use the period symbol instead of the file name to add all the files to the staged area. And once all the files were moved to the staged area, you can see all the files are highlighted in green. Since all the files are staged, we can finally commit these files using the command git commit. And we can add a message by typing -m and in double quotes type the message and then hit enter. And now when we try the git status again, we can see all the files are committed correctly and we have a clean working tree. So far, all the action that are performed is stored in our local machine. But working on a team with multiple talents would be a hassle if we have all the files only on our local machine. To solve this, we can either zip the entire folder and send it to the developers through Google Drive or Dropbox. But again, this would be a huge struggle tracking all the zip files and constantly uploading and downloading. This is where GitHub comes into play. GitHub can store this initialized folder as a repository and make the collaboration with other developers much easier. Here we can connect a remote repository with our local machine, and Git will perform all the synchronization of files between the local machine and the remote automatically just with a few commands. First, we need to create an account in GitHub to create a remote repository. Once that's done, you can click on the plus icon and then click on New Repository. And under the repository name, we can give our project name and fill in the description. Once that's done, just click on Create Repository. This will create an online repository. Now to bring your local repositories online, use these commands generated by GitHub. Now this will bring up a pop-up to log into GitHub. Now use the option Sign in with Browser. And here click on Authorize Git Ecosystem and enter your password. And then click on Confirm. Once that's done, you can see our local files are successfully pushed to online repository. We can double check this by going to the GitHub platform. And here we have the repository that we created on the local machine. With this, we have successfully set up an online platform where we can collaborate with our team members. To better understand, let's try to use some real-time example. We'll add more characters to the scenario from the previous video. Apart from the PCB designer, let's include an electronics engineer for the documentation or coding and a mechanical engineer for external casing for the PCB. This team looks pretty solid. Feels like they can literally do anything. And by now you should have an idea how we can initialize and add commits in Git Bash. Now let's see how we can create and check out various branches. But before that, let's create a circuit in KiCad. To keep things simple, I'll use the same circuit from the previous video. And then I'll just perform a commit. Now from the client we know that we need two versions for this PCB. One is based on through-hole technology and the other one is based on surface mount technology. So in this case, I'll create two different branches, where one branch is dedicated to the THT version of the PCB and the other branch is dedicated to the SMD version of the PCB. Use the command git branch followed by the name of the branch. In this case, I'll name this THT_version. And to see if the branch has been created, use the command git branch. And we have two different branches. One is the main branch and the other one is the THT branch. Now to check out to the THT version, use the command git checkout THT_version and then click on enter. And here we can see we are currently in the THT version branch. In this branch, we can assign all the through-hole components to these symbols. If you're not sure how to do that, click on the I card on the top right to learn how to assign a footprint in KiCad symbol editor. Once that's done, I'll perform a commit. Now similarly, I'll place the components on the PCB layout editor and route the components. And I'll commit whenever necessary. So I can go back in commit tree and check if something went wrong during the development. While I'm working on this PCB layout, the electronics engineer is free to use the main branch to submit their documentation files based on the circuit, since the circuit has been finalized by the client. So the THT development is done. Now I can push this version to the online repository by using this command. And when you go back to the GitHub, you'll have a compare and a pull request. Click on this and then click on create pull request. Now when I go back to the repository's homepage, we can see here we have two different branches. One is the main branch and the other one is the THT version branch. Seems like the other developers have also included the documentation and the mechanical parts in the main branch. Now, when I check the same in my local machine, there is no documentation nor the mechanical parts because we haven't synced our local repository with the online repository. Just like how we use push command to send the data from local repository to the online one, we can use the pull command to get the data from online repository to your local repository. Everything seems good. We have the local repository reflecting what's happening on the online repository. So let's follow the same process and create a SMD branch and complete the PCB. Now let's push the SMD branch to the online repository. So we'll use this command. Since the SMD version is finalized, let's merge the SMD files to the main branch. We can do that by using the command Git Checkout main, and here we can use the command Git merge SMD version. Now we have merged the SMD branch to the main branch. So let's push this change to the online repository. To better visualize how the commits and the merging of branch works, we can either use Git GUI or we can go to GitHub and click on Insights, and under Insights, click on Network. Here we'll have a better visualization on when the branch is created and how the branch is merged. After merging the SMD branch to the main branch, I'll check again if the PCB layout is ready for manufacturing. Once everything seems good, we can just generate a Gerber file for the manufacturing process. It is sometimes okay to create Gerber file and commit it to the repository as usual. But again, tracking various Gerber files or zip files would be difficult with Git. So Git offers few other features that are used to maintain the build files and the finished project files. These are called tags and releases. To do that, go to GitHub and click on Create a new release. And under this, click on Choose a tag, and I'll name this version 0.1.0 and then click on Create new tag. If you are new to software development or to Git, this numbering system might be a little arbitrary at first, but I'm following the semantic versioning to name the tags. So if you like to do the same, I'll drop a link in the description which will explain about semantic versioning, or you can read more about this in the link provided by GitHub. Anyway, once the tag is created, I'll name this release and write a small description of what we did in this release. And under this, we have the option to attach the Gerber file. We can follow the same process to have a mechanical part as well, but to keep things simple for this video, I'll just stick with Gerber file. Once everything is set, just click on Publish Release. With this, we can track when the Gerber was released and at what version of the PCB development the Gerber was generated. We successfully connected GitHub with KiCad, along with various features provided by GitHub. Managing KiCad projects can get out of hand very easily. That's the reason we made last two videos discussing how to manage KiCad projects effectively using Git and GithUb. Similarly, managing KiCad external libraries can be cumbersome when you try to use the same library collection over multiple projects. So in this video, we'll see how we can fix these issues by using Git Submodules. Before starting, make sure you have a local Git repository in your machine with a custom footprint symbols that you like to use. Then make sure this repo is hosted online and synced with GitHub. In this video, we'll be using Git's very less known feature called Git Submodules. This will help us link one repository to another repository as a dependency. This way we can avoid or at least reduce a lot of time in developing the same footprint and symbols. And also this will make the library centralized for all the project that we'll be working on. This way we can make the changes to footprint and symbol only once and it will be reflected in all the projects. Anyway, let's see how we can implement this in KiCad. We'll be using this project from the previous video where we have the circuit, PCB layout and a lot of versioning going on. Now to create a submodule for this project, open the project in the File Explorer and then open Git Bash. Here use the command submodule add followed by the library repository link. And we'll add the path where to download this submodule. I'll use this path. With this, we have the external library setup. Let's import few of them and try it out in KiCad. Open the schematic editor and then go to Preference and click on Manage Symbol Libraries. And here click on Project Specific Library and here add the path to the symbol by using the plus icon. In my case, this is my location. Seems a little too long. Also, if I try to push this to GitHub, anyone who likes to open the project won't have access to the same path in their system. To solve this, KiCad offers a few keywords which can be used. In this case, I'll use the keyword KiCad Project mod. Let's quickly check if this works. Yes, we just added the symbol successfully. We can follow the same process on PCB Layout Editor to add footprint to the KiCad project. With this, we have linked our library repository with our project repository. Let's push this change to GitHub and see how these files are updated in the project repository. Here we can see a new file called .git modules is added. And when you open this file, you can see we have the URL to the KiCad library project. And when we open the URL, we go to the library repository. But how does adding a library submodule help? Well, first we'll have a centralized location to dump all our custom footprints and symbol and reuse it in multiple projects. Then any mistakes in footprint or symbols can be fixed once and it will be automatically updated on every project. Finally, it's a great way to collaborate with a large team who are working on a large number of projects. This is not necessarily the best way to manage and handle library files. There are other options like maintaining your own database or using a dedicated third-party application. But if you are anyway using Git and GitHub in your workflow, this method would make it much easier to maintain and share your KiCad library files. Version control is kind of hectic in hardware engineering. But we tried to solve this issue by using Git and GitHub, and they seem to work well to a certain level. But this won't be just enough for hardware engineers. Even though we can see the changes and various versions, it's hard to see what's the difference between previous version and current version of the circuit without toggling back and forth. To solve this issue, in this video we'll use Cadlab.io, which lets us see the version difference in real time along with various collaboration and annotation tools. Anyway, let's start with signing up for Cadlab.io. Here I'll use the GitHub to sign up, so it will be a little easier later to integrate Cadlab with existing GitHub repositories. Once logged in, we'll have a demo project with a guide explaining the features of Cadlab along with how to use them. But in our case, we'll try to understand Cadlab interface and features using our custom project. So I'll skip the tutorial and then click on Create Project. Here, let's give the project a name and some description. For ownership, I'll select personal, and for access, I'll select public. Unfortunately, on free version of Cadlab, we have a very limited number of private projects, but it can be upgraded with a paid version. Now finally for the repository, I'll skip the first two options and select this because I have already hosted the project on GitHub. Now to give access to Cadlab to access GitHub repository, click on Authorize. And once the authorization is done, make sure you select the repository that you want to link and then click on Create Project. This page looks very similar to GitHub. On the top, we have the branch selection, we have all the files and folders listed here, and finally, README file for the project. Now what makes Cadlab unique is this section, where we can see the PCB layout file, schematic file, and library files without the CAD software that was used to create it. This feature is excellent and allows us to share the file to someone for a quick reference or for a quick review. And yes, This feature not only works for KiCad but also works with Altium and Eagle as well. Anyway, now let's dive into all the features of Cadlab, starting with branches and history of change. To do that, go to Branches. This feature is very similar to GitHub, where we can see all the branches of the project and also commit history of each branch. But Cadlab is unique in showing the changes unlike GitHub. It can show the changes on a visual level with an interactive window to see the changes of the tracks, components, symbols, text, and everything that's related to the project. To open up the visualizer, select any one of the branch and click on Changes. And then click on Visual Changes. This visualizer can be used to see the difference between previous and recent commit without going back and forth between KiCad and Git. Since the Cadlab rebuilds an entire file rather than just taking a snapshot, this lets us access various layers of the PCB without using a CAD software, which is a pretty good feature. Along with this, the visualizer can be used to see the difference between two branches as well. To do that, go to Branches and select the from by using this button and use this button to select the two and then click on Compare. And then click on Visual Changes. With this, we can see the various changes that's happening between two different branches. And we can see all the changes that happened during the development under the change list. Now, apart from this feature, we can use the visualizer to mark and annotate for better collaboration. Let me show you a quick example. Let's say we want to change the size of the LED from 5mm to 3mm. I can use the annotation tool and click on Annotate, and I can draw an outline around the LED. And then I can add the message that I want to convey for the developers. And once the request is done, you can just click on this icon here. This will resolve the annotation, which means the feature is successfully added to the PCB. Already this provides a very decent amount of features for version control and visualization. But having visual collaboration pushes Cadlab one step ahead of GitHub for hardware engineers. Unfortunately, there's only so much features that we can use on the free version of Cadlab. If you like to use more features of Cadlab, check out their pricing page, which mentions all the features they'd be providing along with their Pro and Teams plan. Anyway, this completes the KiCad version control series. If you like to read more about Cadlab, please check out the article we have written on cadlab.io. If you like this kind of video, make sure to subscribe to the channel to see more interesting content related to KiCad. And if you have any questions or doubt, please reach out to us at PCB Cupid Q&A. Until then, keep learning and keep creating.